This lesson is on the ideal gas equation, and it follows on from the lesson on gas laws, so I advise you watch that one first before you tackle this. However, we left that lesson with the idea that the pressure, the volume and the temperature behave according to this equation. And what we were considering was a volume of gas, and I used a cylinder last time round, so I'll use that one again. Right, so inside that volume it will have a pressure and it will have a volume, and these two behave according to Boyle's law. We also said as well that it has a certain temperature, and we know that they behave, the volume and the temperature, according to Charles's law, and all of them together according to this relationship we have here. However, one thing we failed to mention was the number of particles, and that will have a bearing too. More particles, more collisions will create a bigger pressure. So this constant will have a proportionality to the number of particles. Okay, so let's write that down again. Pressure, volume over temperature is going to be proportional to the number of particles, and therefore our constant of proportionality is K, which is very famous. It's Boltzmann's constant. And it's given a figure of 1.38 times 10 to the minus 21 joules per Kelvin. Remember, this temperature that we've taken here is in Kelvin. Fantastic. Okay then, now a little slight bit of rearrangement will bring the equation to one that we prefer to read it as. PV is NK T. However, this might not be the way in which we want to always use the equation. We might want to use it, rather than talking about number of particles, number of moles. Let me just remind you again how many particles there are in a mole. There is an Avogadro's number of particles in 1 mole, which is 6 times 10 to the 23 particles. Therefore, if I was to want to change this equation into the number of moles, I would need to take my number and divide it by Avogadro's number, which gives me the number of moles. PV equals, but I couldn't just take K in there as well. I need to change that constant of proportionality. And the way that I need to change it is by multiplying Boltzmann's constant by Avogadro's number, and that will give us R. Let's work out what that would be. 1.38, I've got Boltzmann's constant, multiply by Avogadro, and it comes out to be a very famous number, 8.314 joules per Kelvin per mole. Just get another pen. Per Kelvin per mole. And this is known as the universal gas constant. Here we have in front of us now the ideal gas equation. However, it's called ideal because the situations which we set up are rarely going to be ideal. Let me just talk about what conditions are necessary in order for that to happen. If we have our cylinder of gas again, we're hopefully imagining that each particle has a full volume to move around. So it needs, so this ideal gas, if it's to remain ideal, needs a particle to occupy the entire volume. Okay? And the second condition we need is that the intermolecular forces are negligible. Why is that? Well, as one particle passes past another, we don't want it to be deviated and experience a force here. We want to imagine that each particle bounces around the box ideally on its own. So how is it achieved that each particle has the whole volume? Well, we work to a low pressure, And how do we achieve the intermolecular forces are negligible? Well, we want the particles to move past so fast that it's a negligible effect. So we have a high temperature, because we know that temperature implies the average kinetic energy. So the higher the temperature, the faster the particles are moving. Superb. Okay, let's set up our first question. A nice straightforward question. Let's imagine a reaction takes place. And this reaction produces CO2. It's going to produce 0.3 litres of CO2 at a pressure on the Earth's surface, which is 1 times 10 to the 5 pascals, and at a temperature which is 27 degrees Celsius. Just mention there that 1 times 10 to the pascal as the pressure is the normal atmospheric pressure. Okay, and what we want to work out is, first of all, A, how many moles has been produced, and B, what's the mass of gas that's been produced? Okay, if you want to give that question a go yourself, hit pause now. But if not, I'm going to go straight on to the answer and see how you've got on. Okay, the first one. How many moles? Well, let's take our equation that we're familiar with and we've just derived. Let's rearrange this to get the number of moles. And let's substitute into the equation. 1 times 10 to the 5, atmospheric pressure. The volume, though, 0.3. I mean, now this volume in this equation here should be left in terms of meters cubed, and litres is not meters cubed. So we're going to have to do something to that figure. So let me just show you below. We know that 1 meter cubed is the same as saying 100 cubic centimeters, which is 1 times 10 to the 6 centimeters cubed. Now, 1 litre is 1,000 millilitres, and a milliliter is the same as a centimetre cubed. So, therefore, it would be fair of us to say that we could fit 1,000 litres into 1 metre cubed. And I suppose that is the relationship I think you ought to bear in mind. Actually, I'm going to put a big box around the whole of that proof so you know that it's outstanding. Bring that back, therefore, 0.3 litres will be 0.3 times 10 to the minus 3, because we merely divide by the 1,000 metres cubed. We divide that by our universal gas constant and the temperature, which, another little being careful moment here, we have to put into Kelvin. And if we do sums, that comes out with 0.01 of a mole. Fantastic. Okay, then B. What's the mass of the gas? Well, nice and simply here. Something that I didn't tell you right at the start, unfortunately, was that CO2 has a molecular mass of 4.4 times 10 to the minus 2 kilograms. Okay, so coming back down here, what's the mass of the gas? Well, if each mole has 4.4 times 10 to the minus 2, then you merely multiply the molecular mass by the number of moles to give you the mass. In this case, 4.4 times 10 to the minus 2, 0.01, giving us 4.4 times 10 to the minus 4 kilograms. Or, if you like, 0.44 grams of gas. Okay, fantastic. Now let's change it to very slightly, give another little level to this question. Let's imagine that gas, let's imagine now the gas was collected at a pressure, so it's a higher pressure it's being collected at. It's being reduced in temperature, and we want to find out the volume. You could press pause here and give that a go yourself. However, if you are happy with carrying on and watching the solution, here it comes. Okay then, so take the ideal gas equation. We rearrange it to find volume. We know the number of moles from our previous answer. And this time, now we're going to work to minus 13 degrees in Kelvin. Also increase the pressure greatly. So, I mean, intuitively you should understand that you've increased the pressure, you're squeezing it more, and you're cooling it down, so the volume should be considerably smaller. And the volume in this case comes out to be 7 times 10 to minus 5 cubic meters. Excellent, right. One more question I think I will pose to you. Let's imagine we have a gas cylinder, one of these breathing cylinders, scuba diving breathing cylinders. And if you've ever been scuba diving, I'm pretty sure that it's about a 20-litre tank. And also, on the indicator here, it tells you the pressure it's running at, which it says 200 bar, 200 times the pressure at the surface of the Earth. Good. So let's imagine you've got it at 27 degrees. You're somewhere tropical. You're scuba diving. What I want to know is how many moles of gas. That's the first bit. How many moles does that cylinder contain? The second part, what is the mass of gas? Fantastic. Do you think you can give that a go? Go ahead and do so. If not, I will just place in the answers now. Okay, so the answer to part A. How many moles? Let's start with our ideal gas equation. Rearrange the ideal gas equation. It's quite a substantial amount of volume, quite a substantial pressure in there. 20 litres again, and because it's litres, to change it to meters cubed, you must divide it by 1,000. Divide that by the universal gas constant, and of course the temperature in Kelvin. And this gives rise to 160.4 moles of gas. Now that seems quite substantial, but it needs to be, because I don't know if you're familiar with scuba diving, but scuba diving, that tank, that 20-litre tank, on a reasonable scuba diver should last for about, 30 to 40 minutes at reasonable recreational diving depths. And if each breath takes, say, 5 litres, you can imagine how many litres must need to be crammed into that cylinder. Okay, what about the mass of gas? Once again, the mass is going to be the molecular mass multiplied by the number of moles. Once again, I forgot to tell you the molecular mass of the gas. However, if it's breathing, then majority of it's going to be nitrogen, 70% of it. So let's imagine that it is nitrogen. So let's just say N2, which is going to be 0.028 of a kilogram per mole. So that gives rise to 0.028 multiplied by 160.4, 4.4 kilograms, which is fairly substantial. But then again, it's true that when you run out of oxygen, you start to become much more buoyant while scuba diving. Superb. Okay.